Hello everyone, welcome to ExamRat. My name is Shatabdi and I'm a second year medical student. Today we're going to be talking about a chapter from physics called Work, Energy and Power. In case you've missed our previous chapters, you can easily just go to YouTube and check our previous chapters out. They're all for free. And do subscribe and like us. Thank you. Okay. So, growing up, we've used this term work in a lot of contexts, right? Like, I'm going to work, or I'm going to cook, which is also we've considered it to be work, or anything that we are doing. We have always put the word work in it in some way. We've used it as a verb, but in physics, it has a different significance. It has a different meaning altogether, which is important for us to understand because it is important for us to calculate the amount of work that an object does. And why is it important? Because when we make huge machines which do a huge amount of work, we have to calculate how much the machine can work, right? How much work we have to do on the machine and how much work the machine, how much output it will uh, give rather. Okay. So that is why it is important for us to know the physics that is related to the term work. And with work, energy is kind of synonymous. And then we'll also talk about power, which is nothing but the rate of doing work. Okay, so let's go over the definition here. Work done by a force acting on an object is equal to the magnitude of the force moved in the direction of the force. Okay. So it is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Very simple. So force into displacement. Now, even though it is mentioned here that the object is moved in the direction of force, we think that it might be so that that work is a vector quantity, right? But actually it isn't. Work has only magnitude and has no direction. And when we say that something has no direction, it means that it is not a vector quantity. Now, it's not like that it does not move in any direction. It is the definition doesn't mean that. It means that it does not depend on the direction of the force and the displacement. It is not affected by it. And why I am saying this, we'll understand it a few minutes later. For now, let us just concentrate on the formula. Work done equals to force into displacement, or F into S. S we know that is the symbol for displacement. Okay, so here are some examples of work. In the first example, it is clear to us that the man is doing, like, exerting some force on the wall. Okay, but is the wall moving? I don't think it is, right? And it is very clear from this picture also that it's a heavy wall and it is not moving. So the moment it is not moving, even though we are putting a huge amount of effort, still we are unable to move the wall. So will there be work done or not? Let's come to this later. Okay, second, here the man is taking some luggage on his head and is moving. Let's just assume that he is moving in the forward direction. Since it's not a 3D picture, we can't understand it. Okay, so just we can say that the force is being applied upwards and the displacement is happening in the forward direction. Okay. And in the third picture, it is very clear that the man is pulling the trolley and the girl is inside the trolley. So the man is also moving forward and the trolley is also moving forward. The direction of force is not exactly linear, is it? It is at an angle. Okay. So in all these three cases, the work is not going to be equal to just force into displacement. There are other aspects involved here. So for example, in the first example, even though you are putting a huge amount of force, you are not causing any displacement in the wall. So if displacement becomes 0, then work done will automatically become 0. So in the first case, work done is 0. It's It's a little disheartening, but it is actually the truth. Okay, so here the displacement is in the forward direction and the force is being constantly applied in the upward direction. Okay, here also, since the angle that they make is 90 degree, the work done is 0. Now you might ask why. It is because of a simple reason that we're going to talk about in a few minutes. Okay, this portion, what is it saying? It is saying that the work is done in the forward direction, right? But we are seeing here that there's a certain angle involved, right? So we can't just simply do force into displacement here, right? Because for this to happen, you have to make the force and the displacement in the same direction, right? Like, how are you going to multiply something that is one component is like this and one component is like this? You can't multiply these two quantities, right? Like, yeah, if the whole product would have been a vector quantity, then we would have multiplied two vectors, right? But we are not being able to do that because we know ultimately work has to have no direction. It does not have a direction. So we have to basically make work scalar. Even though force and displacement are individually vector quantities, we still have to somehow not make work a vector quantity. We have to make it scalar, and for that we have to take either a component of force or a component of displacement. Now what is a component? That we'll discuss right now, and then only you'll understand why I said in the second case that work done is 0. Okay, so yeah, so for example, let's just take this example. Like, this was the third case, right? So let's just talk about this example. Here it is given that D or S equals to 30 meter, well and good, and force here, the magnitude of force is 50 Newton. Now what I said in the previous slide was that you have to somehow make the component of force parallel to the component of displacement. Now you know that when we calculate a vector quantity always has a sine component and a cos component, right? So if this is F, you know, and this is theta, then you know that this is F cos theta, and you know that this is F sine theta. Okay, so now we have gotten a component of force in the direction of the distance or the displacement, sorry. So now the thing becomes very simple for us. Now what we do is we simply calculate work equals to it is actually, even if I have given a multiplication sign here, it is not a cross product. It is actually, when we multiply two vectors in this case, since the product is scalar, we can't give the multiplication sign anymore. We have to give dot, because it is a dot product. Why is it a dot product? Because the final product is coming scalar. Okay, so this is, we have changed the, or if it is easy for you, you can also write F cos theta into S. It's the same thing. Okay, so now since we know that the value of theta here is 30, we can just put that F into cos 30, which is half, into S. So here we know that the value of F is 50 Newton and half into S is 30. So we just multiply it, 750. Okay, now about the unit. The unit of force is Newton and the unit of displacement is meter. So Newton meter, but we don't write it as Newton meter. Work has a unit of its own, which is known as Joule. So what is 1 joule? 1 joule is the amount of work done by an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Along the line of action of the force is important because ultimately we have to get both the displacement and the force in the same direction to be able to calculate the work done. So 1 joule is equals to 1 Newton into 1 meter. So here work done is 750 joule. So now you've understood that the modified equation of work is actually Fs cos theta, right? So now I think you'll be able to understand why I said that in the second case the work done is 0, because when we put 90 degree in place of theta, what will it come? It will come Fs cos 90, right? And you know that the value of cos 90 is 0. So work done becomes 0. This is also a disheartening case because we know how much coolies, like how much force or how much effort it takes for them to put luggages on their head and to walk for miles. But in physics, the total amount of work done is 0, but obviously the mechanical work that the man is doing, the manual labor, it is a lot. But in physics, it is not quantifiable. The amount comes to 0. Okay. So since we've talked about work now let's come to energy. Yeah. So energy is also very synonymous to work. It is measured in the term of its capacity of doing work. The unit of energy is therefore obviously the same as that of work. It is joule. So we can say that 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy is required. It is known as kilojoule. Nothing difficult. 1 kilojoule is equals to 1000 joules. So the capacity to do work. Okay, so energy is not exactly something that you can calculate. Since you're calculating work, energy is something that we use to describe how much work is being done. It is subjective. It does not have its own unit. It does not have its own definition per se. So instead of using using the term the work done here or the work done here, instead of using this term, we use the term energy, like the energy required by this machine to give this output, or the energy required to do this lifting, to do this weightlifting, to run the windmill. So it is just a way to define the capacity of doing work. Nothing difficult. Okay. So energy can be of various forms, right? So the reason why the term energy was created so that we can describe a lot of ways of doing work. Okay, so for example, you know that the light that comes from the sun, we call it as light or solar energy, right? Okay, the energy that comes that the windmill basically uses to produce electricity is basically wind energy. That obviously turns into electrical energy later. Yeah. So if you're throwing a ball, you're doing mechanical work. So it is called mechanical energy. So now you're understanding that the definition of work, or only using the term work in every aspect of life, was not easy, was not very fluent. So we came up with something that generalizes that brings out a big bubble under which we can put a lot of other quantities, right? So that's why we came up with the term energy, which will give us a definition of a lot of things together. So light energy, wind energy, electrical energy, mechanical energy. There are other forms also. There's sound energy. All are types of doing work only, right? So we are just measuring the capacity to do work in a different way by just addressing it as energy. Okay. So here we are going to talk about kinetic energy. Now what is exactly kinetic energy? I told you about mechanical energy, right? So basically it happens so that mechanical energy can be of two types. One is kinetic energy and another one is potential energy. Okay. So in this slide we're going to talk about kinetic energy. What is it? So basically in one simple way, the kinetic energy is anything that we quantify by saying that the amount of motion that the object does. Okay. So anything, an energy calculated on its motion aspect is called kinetic energy. So a moving object can do work. An object moving faster can do more work than the identical object moving relatively slow. Okay, so by this line we understand that a slower object will do lesser work or will use lesser energy than an object doing the same work at a faster rate. So it means that kinetic energy somehow depends on velocity. Now, how does it exactly depend on? We'll learn later. Okay. So a moving bullet, blowing wind, rotating wheel, speeding stone, all of them are doing work, right? So when we have talked about in our previous chapters in motion, how we've talked about the bullet piercing through the glass wall and having a huge impact on it. So we have calculated the speed, we have calculated the time it takes to um, push through a wooden block and get stuck in it, how much distance it travels. We have talked about the recoil velocity, right? But we have not talked about the amount of impact that it does or the amount of energy that it spends to pierce through that glass, and that is what we are going to calculate here. So what I said, objects in motion possess energy and we call this energy kinetic energy. Okay. So we realized that kinetic energy obviously depends on velocity, and also we know that impact means that it is somehow related to momentum as well, right? So since momentum is already dependent on your mass and velocity, so another thing that the kinetic energy depends upon will be mass. Okay. So what we get from here is that kinetic energy is somehow dependent on both mass and velocity. So now how is it related? It's basically the formula of kinetic energy is half mv square. Okay. So here are some examples of fast moving ball breaking a glass window pane, as I told you with the bullet. Okay, a swinging pendulum actually it represents both kinetic energy and potential energy. For now, let's just keep this example on hold. A flying bird, it will possess kinetic energy. Anything that moves, it will have kinetic energy. Okay. So here is another better definition. Here it's written that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Okay. So from here we can also understand that the work done is to change its velocity basically is kind of how we calculate kinetic energy, right? So basically Wf minus Wi is kinetic energy, or the energy required to change the velocity or to change the initial velocity to a final velocity, whether to decrease it or to increase it. Now how you are doing it? By doing some work on it, right? That is how you are changing the kinetic energy. So this is an important formula. Okay, so yeah. So now we know that the formula of kinetic energy is half mv square. Okay, and also we know that the difference between, or the work that is done to change the velocity of an object, is basically the kinetic energy that the body will possess then. Okay, so yeah, so no, I'm sorry, this will be different. Okay, yeah, so basically in this slide we talk about the proper definition of kinetic energy, which says that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Now it basically says that if the initial velocity, like if we write vi was something and then we did some work on it for it to acquire final velocity, we are basically saying that kinetic energy final minus initial kinetic energy is equal to the work done, right? Or half m v f square minus half m vi square equals to work. So now this relation between the work done and how it brings about a change in the kinetic energy by actually changing the velocity of an object, this relation is very important. Okay, so another thing that we have to remember is that I had told you in the previous slide that since kinetic energy is something that possesses motion and it depends upon mass and velocity, so it has to in some way be related to momentum as well, right? So how can we write that? So we know that kinetic energy is equals to half mv square. Okay, so now you know that momentum is actually mass into velocity, right? So what we can do is half m, we can basically here replace the v by writing v equals to p by m, right? So let this be equation 1. So here if we insert equation 1, it will basically be p by m whole square, right? So I'm just changing the color. Yeah, so here basically ke becomes equal to half m into p square by m square. Here cut the squares, so it's basically coming to that k equals to p square by 2m. So if someone asks you the relation between kinetic energy and momentum, you're going to be able to, I'm sure, write this formula, like this is the exact relation to it. Okay. Also, you know that mass is constant, right? So when I say mass is constant, you can also say that if k equals to p square by 2m and this is constant, then k is directly proportional to p square, right? So why am I saying, why are we discussing about this, is because there are questions where it is asked that if momentum decreases or is reduced to half, then how does it affect the kinetic energy, or how does the kinetic energy change? So here you can basically write that kf in when we discussed the exercises in gravitation, also we had used this concept where we calculate the final we calculate the final thing, then we divide it by initial to show a relation between them, and that is how we show how the changes happened or how much the changes happened. In the same way, first we are going to see like ki is equal to p square and kf is basically p by 2 whole square, so it's basically p square by 4. Now if we divide the final kinetic energy by the initial, we'll get what? We'll basically get p square by 4 divided by p square. We know they are going to get divided to each other equally, so kf becomes 1/4 of ki. Right. So it is, since it is directly proportional to the square of momentum, so if momentum gets reduced by half, kinetic energy will get reduced by 1/4. So all these concepts discussed today were very simple, and if you have any problem, you can obviously comment in the comment section below, and if I went fast anywhere, you can just pause the video and like go back and like write the definitions or understand it better. So that will be all for today. In the next class, we're going to be discussing about potential energy, how we calculate it from a height. We're going to discuss about the conservation of energy, and lastly about power, and end the chapter. So that will be all for today. Thank you for listening.